Can you hear me? Okay, so I would like to start saying a little bit. I don't know why I get this feedback. Let me use sound. I would like to reiterate a little bit on why we started this collaboration. Where did we start? And first of all, I would like to say that, well, we can only improve what we can measure, and this is if we want to enhance the water productivity in the region, then we really need to have the tools to be able to measure the water consumption of the crops, not only in irrigated crops, but also in rain-fed crops. Therefore, being able to calculate the water productivity at regional scale. But what we found when we started the project, first of all, we need a simple tool to be able to determine the water use. Unfortunately, there were not cost-effective tools for transpiration, because most of the scientific grade equipment you can already appreciate they are far too complex or expensive and limited to a number of locations where they could be available. And also the need for the validation of regional evapotranspiration products, as Keith has just presented, are to have some ground data to validate the observations for the satellite, but also the estimates from the evapotranspiration. So a little bit of history, how where we are at the moment. So we need to understand how we all started. So there was this initial workshop in Cordova in July 2018. I know a lot of you that are there were already in this workshop. And at that time, we were discussing how we could calculate evapotranspiration in our locations. And I remember that time, we presented the traditional methods, and I presented some of the new technologies that we were developing in other projects. And IHAB appreciated that it would be quite powerful to have these simple, cost-effective tools in these countries. And we just started working on the development and the validation of the initial prototypes. So just a couple of weeks later, we started testing some of our prototypes, both the sensors, comparing with standard commercial scientific grade equipment, the weather stations, and we produced our first prototype in December 2018. And it was February 2019 where we did our first deployment in Algeria. That was the very first prototype. It was clear at that time that we had to make some improvements in the energy management. So we made our first iteration with the gateways and the solar power and so on. And it was in April 2019 when we first deployed our second version of the prototype in Egypt. Then it was clear that we had to build this community and we had to train people with very little or no experience in electronics to be able to reproduce, to replicate the sensors in their own countries. And we had our first technical workshop in September 2019. Again, a lot of you may be there at that time. And it was a great experience because we learned people how to manage the electronics, how to program microcontrollers, how to calculate ET, and so on. And since then, we have had a number of online webinars, training sessions, as well as hardware revisions based on your feedback, field visit, bus stopping. The D groups have been populated with the manuals and questions, as well as different WhatsApp super groups that we have created for every country. But I think for me, the biggest relevance of the project comes from the community that we have built and the capacity that we have built with the different partners. This has been an iterative process from the initial prototypes, with the training, with the initial deployment in the fields, the data collection and field validation, including in this, as you would see in this workshop. But in every process, we have gathered feedback that have helped to improve the next version of the prototypes. And we have done this about 4 times right now. So also we have trained different people in the countries. There are more than 25 technicians trained in 8 different countries, not just the 6 countries of the ET network. And I think this is really important because thanks to the feedback that we have been gathering, we have been improving the failures and the issues that we have been identifying. So you can see in this picture, this is how the first air temperature humidity sensor came back from Algeria. So we changed them, modified the version to include some protection and better coating of the electronics. Then we can see how the top pyranometer looked like after a couple of years. Again, all the electronics internally were damaged and not functioning. So now we have moved from a completely do-it-yourself device to a more robust system using ruggedized instruments and more commercial instruments that are still commercial grade, but more robust and more reliable than what they used to be in the past. So the current solution right now consists on a sensor package with at least 4 sensing nodes with air temperature and humidity, the canopy temperature sensor, as well as the soil temperature sensor. Like I mentioned before, all of these have been upgraded to be more robust, as well as the electronics that now are more turnkey, so there's no soldering involved. It was at the very beginning. Still, there's some drilling and manufacturing involved for the construction of the nodes, but overall, we have made huge progress here. Also, we identified the problem with the pyranometer data from the weather station. So now we provide a pyranometer node with a commercial pyranometer that provides high accuracy, reliable data for the solar radiation. And the base station have been also improved with a fully integrated gateway and 4G modem. So instead of having multiple instruments, we only have one that includes everything. And there has been also some important changes in the commercial weather station that is used at the moment. So, so this is the sensor package that we call Cordova IT, which stands for Conductance Recording Device for Observation and Validation of ET, not just the name of our city. It's very important to mention that all this development is completely open source, both for the hardware design, but also for the software, for the gathering of the data, for the analysis of the data. Everything is open source and available on GitHub. The system has been designed to be completely modular and scalable. So the reason why we have 4 sensing nodes is that we should be able to monitor the heterogeneity, the spatial variability of the fields. As Ajit has mentioned, this is very important because with 4 nodes, we can characterize a little bit this variability, not just in one single location. Also, it allows us to monitor different crops or different irrigation treatments at the same time, simultaneously. And we can have more than 4 sensing nodes. This is the standard kit, but this can be updated to hundreds of nodes if required, okay? The idea was to keep the cost as low as possible. And obviously, we are still in a prototyping phase, so it's not the cost of a commercial sensor or scale-up construction. So the total cost is about 4,000 euros, including the shipping and all the logistics. And there are also some open source developments that are very important for the project, like the OpenCropLib library for the calculation of ET, actual ET, ET0, etc., as well as the web-based visualization interface that you are probably already very familiar with. So just a brief description how the ET is calculated with the energy balance. So basically, we calculate the sensible heat using the temperature, the difference between the canopy and the air temperature, and different algorithms for the calculation of the aerodynamic resistance that requires some knowledge of the canopy height and the canopy structure, and some models for the calculation of the net radiation. Basically, we calculate the evapotranspiration as the residual between the net radiation, the soil heat flux, and the sensible heat. For the daily calculation, H is normally neglected as recommended by FAO 56, but I would like to mention that G is calculated for the hourly estimates as a fraction of the net radiation. That depends whether we are during the day or during the night. So basically, we calculate the latent heat, and then we can calculate what is the equivalent to water evaporation. It's very important to mention that this makes some assumptions, for example, in terms of albedo, in terms of the partitioning of the radiation. So basically, we assume that we are looking at pure vegetation for this calculation. So this doesn't work very well when we don't have full canopy cover, or when we are looking at part soils and part of vegetation. So the data is freely available and is open for everyone to visualize and explore into this Grafana interface, this cordova.csic.es. You probably are quite familiar with this for downloading, for visualization. And then you can follow the download tool, which is this simple web interface that allows you to select your deployment, start date, end date, what is the download data format that you want. And then you get the CSV files that with all the ET and all the intermediate variables like sensible heat, G, and everything is calculated as a spreadsheet. But also there are more applications and libraries that you can use, like I mentioned before, this OpenCropLib. You can use this one for calculating ET0 or actual ET, and there's some examples on the repository. Basically, it uses Python as a way to calculate, and this is basically which is under the bonnet for this download tool and all the calculations that we do. But as Domitir mentioned before, we know that we have had some issues. There have been some issues with obviously the electronics, but sometimes there are also common issues that can affect the quality of the data, and I would like to highlight some of these. I know that we have made a lot of mention of this in previous webinars, but I would like to reiterate how important is to make sure that we understand what we're measuring. And for example, some common issues that we have identified in the past, especially in summer crops with tall crops like maize or sorghum, is that sometimes the weather station is buried inside the crop. So obviously this means that the wind and the radiation and all the other variables that are required for calculating ET0 are not valid anymore. The weather station should be installed at a standard height, like 2 meters, not as short as you can see in this picture, away from any obstructions for the wind and the solar radiation. This is very important also for the pyranometer node. Also, we have found that in some cases, the canopy temperature sensors were looking at the ground, not really at the top of the canopy. Again, this invalidates any calculations that we made of the energy balance. Or sometimes we can find that the sensors are covered with a spider web. So we are measuring the actual temperature of the spider web, not the temperature of the crop. And again, this is affecting any calculation that we made. So just a few key considerations. I would like to make a lot of emphasis. So please use the latest version of the stations that you have. As I mentioned, we are in the 4th iteration. A lot of the weather stations that have, all the new weather stations that have been sent have been modified to improve the accuracy. Same thing with the pyranometer nodes. So a lot of the data that has been reported is with the previous versions, and I think some of you may already have some new stations in your offices. Please contact us if you need any help and deploy them in the field for new campaigns, because otherwise we won't be able to have the best quality of the data from this system. Also, please document, coordinate sensor heights, take photos and share them with us, because this way we can also identify some potential issues in the field before it's too late. Maintenance is essential. Like with any other instrument, it's very important to keep the pyranometer clean, remove spider webs, dust, etc., prevent any ingress of water, because water and dust are the worst enemies of the electronics, as you probably already know. There are a lot of issues with the data continuity. As Ajit had mentioned, there are sometimes data gaps, and sometimes it's not because of an instrument problem. It's sometimes a human factors, as simple as recharging the SIM cards. So sometimes it's just to have a reminder to tell us that we need to recharge and avoid having loss of communication. And also it's very important to make sure that when you download the data for reporting, you perform a minimum quality assessment and quality checks. So for example, please remove incomplete days, non-nominal values, etc. So for example, negative values are clearly an instrument issue, or if we sum the evapotranspiration from the hourly data, we need to make sure that we sum the complete day, not just incomplete days, because otherwise we can get to unrealistic values that go to the report or go to the L1 or L2 data levels, and this is not right. We should avoid this with just a minimum check of the data. So just to finish, a bit of a summary of the results. As I mentioned, we have 4 major revisions of the system, and going from a complete do-it-yourself 3D printed system to almost a commercial turnkey kit. We have deployed this in 8 different countries and tested in different crops, and now including 3 crops, as our colleagues in Tunisia are doing at the moment with olives and palm trees. So in total, I think it has been about 21 kits that have been shipped, and most of them deployed already. For the validation data, all of the data, raw data, is freely available on the Grafana website, and we are working closely with ICARDA for the collection and validation of the data sets in the NENA region, as you will see in the next presentations. And we also have a couple of campaigns here in Cordova in 2020 and 2021. And I think that the most important thing, as I mentioned before, is the capability building and building these technical skills for the different partners of the creation of the D groups and discussion groups, technical support groups at the different countries levels. You have available all the training materials, the webinars, etc. in the D groups. I would like again to thank all the feedback that we get from all the users and partners. For the future, I think we should be looking at better dissemination and adoption of some of these technologies, especially for final users, as I mentioned before in my comments. I think that if we involve the farmer field schools and teach them and show them how they could use these instruments in the irrigation scheduling, especially for basic programming based on ET0 and coefficients, would be great. I think there are a lot of potential for integrating some of this data into mobile applications such as iRay, and again, looking for broader adoption beyond the scientific community. I think it's very important that we improve the engagement with the local industry, especially if we want to make more of these kits locally in the countries that are participating, but also with the local farm advisors and agronomists that could learn how to apply this tool for irrigation scheduling. For the future, we're looking at integrating new sensors. So for example, we have prototypes for soil moisture and salinity, canopy height. We're testing new approaches as well for automatic measurement of canopy height. But for this being a collaborative approach, we are very open to ideas and prioritize what are the most critical things, like is it ground cover, is it spectral indexes, what are the key things that can enhance how we calculate things in the future. Also, we're looking at improving the energy balance model for trees and partial canopy, so using a multi-source energy balance model, for instance, or even going for simplified methods such as the crop water stress index that Ajit mentioned before as well, and we are using in other projects. It's a very simple and effective way of estimating the crop water status. So I would like to finalize with big thanks to everyone involved over these years in this development, all the feedback, everyone who came and have come to Cordova, as well as everyone that has hosted us, and Arantxa and Alicia in particular, in the backstopping missions, because as I mentioned before, this is a collaborative project, and I think the reason why it's becoming such a success is thanks to the feedback and support that we are getting from all of you. So thank you very much.